really looked at a car engine or maybe a giant wind turbine and just wondered, what is actually going on in there? Well, there's this entire hidden world of mechanical engineering at play. It's like a beautiful dance of gears, forces, and energy. So today, let's pull back the curtain and uncover the principles that literally make our modern world move.
All right, so here's our game plan. We're going to start with the big challenge. How do you even control power? Then, we'll dive into the building blocks, gears, and see what happens when you put them together in gear trains. After that, we'll switch gears, no pun intended, to statics, the science of making sure things don't break. We'll look at flywheels, which are all about smoothing things out, and finally, we'll put it all together to see this unseen mechanical world that's all around us. So, let's start with the most fundamental problem, right? Imagine you're a machine designer. You've got this electric motor, and it's spinning like crazy, super fast. But what do you do with that? How do you take that raw, high-speed rotation and turn it into something useful? Like, say, turning a car's wheels or lifting a heavy elevator. That's the core challenge we're going to solve today.
And our journey begins with the most basic, fundamental solution, gears. I mean, these toothed wheels are the true heroes, the building blocks of pretty much all mechanical design. They let us transmit and change motion with just incredible precision. First up, we've got the absolute workhorse of the gear world, the spur gear. Its teeth are straight, simple, and it's designed to pass power between two shafts that are parallel to each other. It's incredibly effective, and you will find these things just about everywhere. The only downside, that simple design can make them a little noisy. Okay, but what if your shafts aren't parallel? What if you need to, turn a corner with all that rotational power? Well, that's exactly where the bevel gear comes in. See how its teeth are on a cone shape? That lets it change the direction of rotation, usually by a perfect 90 degrees. Problem solved. Next up is a really special one, the worm gear. You've got a screw, which we call the worm, and it meshes with a gear. Now, its superpower is that it can create massive speed reductions in a really, really small space. And it's got this other cool trick. You can't really turn the gear to spin the worm. It's basically a one-way street, which is a fantastic safety feature in a lot of machines. And finally, let's be honest. Not all motion is about spinning in circles. The rack and pinion is this totally ingenious solution for turning rotation into straight line or linear motion. The little gear, the pinion, spins, and it moves that flat, toothed bar, the rack. You know the most common place you'll find this? Your car's steering system. It's what turns the circular motion of your steering wheel into the side-to-side motion of your tires. So, individual gears are awesome, but what happens when you need a huge change in speed and you need it to happen in a tiny little space? That's when just one or two gears won't cut it. You have to start combining them into systems, and we call those gear trains. So, check this out. Over on the left, you've got a simple gear train. Each shaft just holds one gear. It's straightforward. But look at the right. That's a compound gear train. See how at least one of those shafts has more than one gear locked onto it? This is the secret. This setup lets you get much, much bigger speed reductions with way smaller gears than a simple train could ever hope to achieve. It's all about efficiency. And now we get to the really clever, almost mind-bending stuff. The epicyclic or planetary gear train. In this system, the gears don't just spin in one spot. The axes of the outer planet gears actually revolve around that central sun gear. And why go through all this trouble? Well, their main advantage is getting ridiculously high speed changes in a super compact packet. I love this analogy. It's just a perfect way to picture it. If a simple gear train is just horses spinning on fixed poles, then an epicyclic gear train is the whole carousel. The floor itself is spinning around, and at the same time, the individual horses are also spinning on their own poles. You've got these multiple layers of motion all happening at once. It's brilliant. Okay, so we figured out how to control motion. Fantastic, but that's really only half the battle. We also have to make sure that the incredible forces running through our machines don't just, tear them apart. And that brings us to the science of stability, statics. The whole idea, the core principle here, is something called static equilibrium. It's a simple but powerful concept. For an object to be stable, to not move or break, all of the forces pushing and pulling on it, and all of the twisting moments, they all have to perfectly cancel each other out. Their grand total has to be zero. This is the bedrock rule for designing any strong, stable structure. And this is what that looks like in the language of math. Now, I know it might look a little intimidating, but trust me, the idea is so simple. That first equation just says all the forces going left and right have to add up to zero.
The second one, all the forces going up and down have to cancel out. And that third one says all the twisting forces, or torques, also have to balance out. If you can make all three of those things true, your object is in equilibrium. It's not going anywhere.
So how do engineers actually do this in the real world? They use this fantastic tool called a free body diagram. It's like you mentally take the machine apart, piece by piece. You isolate just one part, you sketch it out, and then you draw arrows to represent every single outside force that's acting on it. It's like you're creating a force blueprint. Let's take this 4-bar mechanism, for example. You might find something kind of like this in a car's suspension system. Now, it looks pretty complicated, right? But by using those free body diagrams, an engineer can analyze the forces in each individual link, one by one, to figure out what's happening to the system as a whole.
And here's the magic. Once we isolate a single link from that mechanism, we can use the forces we do know to figure out the forces we don't know. By applying those principles of equilibrium we just talked about, we can calculate exactly what's needed to keep that piece stable, which in turn keeps the whole machine from breaking down. All right. We have controlled our motion. We've made sure our machine is stable. Check and check. But there is one more huge problem. What if your power source isn't nice and smooth? I mean, think about a car's internal combustion engine. It gets this violent shove of energy only once every 4 strokes. How on earth do you smooth out that jerky power?
Well, the answer is the flywheel. The best way to think of it is like a mechanical battery or a reservoir for energy. It's really just a heavy wheel that loves to store rotational energy. So when the engine gives a big burst of power, the flywheel speeds up a little, soaking up that excess energy. Then, when the engine's in a coasting stroke, the flywheel's inertia keeps everything spinning, releasing that stored energy back into the system.
And here it is in its most famous role. It's attached to the end of the engine's crankshaft. The flywheel takes those violent, jerky power pulses from the pistons and smooths them all out into a nice, steady, continuous rotation. Seriously, without a flywheel, an engine would just shake itself to pieces and stall out between those power strokes.
Now, what's really interesting is that not every machine needs the same level of smoothness. This table shows what's called the coefficient of fluctuation of speed, which is just a fancy way of saying how much the speed is allowed to wobble. A big rock-crushing machine, it can be pretty jerky, so it has a high number. But an electrical generator, whoa, that needs to be incredibly stable and smooth, so it has a very, very low number. The flywheel for each machine is designed specifically to meet these needs.
So, let's bring it all back home. We've looked at all these individual components, but their real power, their magic, is in how they all combine to create this incredible, unseen mechanical world that powers our everyday lives.
So let's just recap the big ideas. Gears, they give us total control over speed and direction. Gear trains let us achieve these huge, complex changes in speed. Static analysis, that's our safety check, making sure our designs are strong enough to handle the job. And flywheels are the great regulators, smoothing out any inconsistent energy. These 4 concepts, together, are the fundamental pillars behind almost every machine you can possibly think of.
So the next time you see a giant construction crane, or you hop in your car, or even just glance at an old-fashioned clock, think about these principles. It's this incredibly elegant system, right? You've got gears taming raw power, static forces holding everything together against unbelievable stress, and flywheels providing a steady, rhythmic pulse of energy. It's like a hidden choreography happening all around us. So now that you know the building blocks, what hitting machinery will you see in the world?